if we take more water than is supposed to, then that water is going to be turned into a toxin. We have learned that in homeostasis, we begin with a loop known as a receptor. So a receptor is going to detect either an increase or a drop, a decrease, either an increase or a decrease in the level of some variable. Sometimes hyperthermia, the temperature is too high. Sometimes hypothermia, the temperature is too cold. Sometimes blood pressure. Hypertension, sometimes a drop in blood pressure. Hypotension, sometimes an increase in electrolyte. Hypercalcemia, hyperkalemia. So the step of detecting an increase or a hyper condition, an increase, or a hypo condition, a drop or a decrease, that's gonna be detected by a receptor. So we have different types of receptors. We have chemoreceptors, and we have osmoreceptors, and we have mechanoreceptors. We have chemoreceptors, we have osmoreceptors, we have mechanoreceptors, we have thermoreceptors, and we have photoreceptors. So all of these receptors are there to detect a deviation in a variable. If things go too extreme, hyper, or if things drop so low, that's going to be a hypo condition. If it wasn't for the receptor, your body will never be able to detect. So the receptor is actually, in essence, a detector. A detector. A detector of what? A detector of an increase or a decrease in some variable. But we have different types of receptors. Chemoreceptors, that's what we're going to be doing today. So an electrolyte is a chemical, like calcium is a chemical. Oxygen, it's on the periodic table. It's a chemical also. Carbon dioxide is a chemical. Magnesium is a chemical. Potassium is a chemical. Sodium is a chemical. So we're going to be looking at how your body is able to balance and achieve homeostasis, that you don't have too much of anything. We're going to be learning that too much calcium is toxic. Too little calcium is also toxic. Too much potassium is dangerous. Too little potassium is also dangerous. So we're going to be looking at the loop. The feedback, the negative feedback loop that restores for us the levels. This concept is very clear. Does everybody understand this first step? The first step is to have a receptor. The receptor is going to detect if something went too high or something went too low. Like the police on the highway. The police on the highway has a detector that detects if you're going too fast or if you're going too slow. Your body has the same thing, but it's for chemicals. So today we're going to be looking at how the chemoreceptors report that there is a deviation, an increase. But remember, we don't want hyper, we don't want hypo, we want EU. So we don't want hypercalcemia, we don't want hypocalcemia, we want eucalcemia. We don't want hyperkalemia, we don't want hypokalemia, we want eukalemia. Now, if you look into this loop, this negative feedback loop, the first step is the receptor or the detector. The detector is going to send this another signal. It's going to send an input. It's going to send an input sensory, afferent, input sensory afferent signal to a control center, and this control center is going to process, integrate, and control this information and generate for us an output. Generate for us an output. An output is motor. Since the input was sensory, then the output is motor. And since the input is afferent, the output is efferent. And lastly, we're going to rectify the problem, and then we're going to activate an effector. An effector. So the effector here is the one who's going to replace for us and restore for us the homeostasis. So let's look at calcium, for example. Let's say we have too much calcium. What do we call that if we have too much calcium in the blood?
Hypercalcemia.
Excellent. So we have hypercalcemia. Well, hypercalcemia is apparently not eucalcemia. This is homeostasis. We want that. This is what we want. But due to some condition, now we have hypercalcemia. So who's going to report that there is a hyper problem? That is it going to be a chemoreceptor, an osmoreceptor, a mechanoreceptor, a thermoreceptor, or a photoreceptor? It's going to be a chemoreceptor because we're not dealing with temperature. That would have been thermoreceptor. We're not dealing with pressure. That would have been mechanoreceptor. We're not dealing with light. That would have been photoreceptor. So now the chemoreceptor is going to report and send an input signal that is sensory, and we're going to send it to an afferent neuron. The afferent neuron is going to go to a processing center, an integrating center, a control center. You know, when you call 911, you want the fire truck, someone else wants the police, another person wants the ambulance. They need to process and integrate where to send the proper output. So your brain is constantly getting a lot of information. It's too hot, it's too cold, it's too dark in the room, there's pressure on the right arm, there is tactile stimulus, there's pain on the left leg. So a lot of different calls are coming to the call center. So there has to be a processing and an integration in the control center that's gonna release an output. So when there's too much calcium, who's responsible for receiving the output? That there's too much calcium, that's dangerous. You know, too much calcium is gonna increase the contraction. You know, calcium is part of the action potential that causes depolarization. We went over that when we did the heart action potentials. Remember, we said that for the ventricular contraction, the influx of calcium is the one that prolongs the diastolic phase and the filling phase of the ventricle. So if you have too much calcium, now you're going to drop the blood pressure because the heart is going to be stagnant in a state of prolonged calcium influx leading to a really long diastolic phase. So that is dangerous. So who's going to detect that? It's the parathyroid gland. The parathyroid gland. The parathyroid gland is responsible for when there is a drop in calcium. But when there is an increase in calcium, it's actually the thyroid gland. There is a hormone known as calcitonin. Calcitonin. So calcitonin is a hormone that is going to be released from the thyroid gland in order to counter this increase in this increase in calcium. It's hypercalcemia. So what's going to happen now? Calcitonin, once it's released in the blood, who's going to be the effector? The effector is going to be the bone tissue. So all the calcium that is too much is going to be sedimenting and building up in the calcium mountain, and that is going to be your bone. So the effector here is the bone. So now what's going to happen to the calcium levels in the blood? Are they going to increase or decrease? When we take all the calcium from the blood and we dump it into the bone, is calcium going to increase or decrease? Calcium is going to. You took calcium from the blood and you dumped it into the bone. Is that going to increase or decrease calcium? That's going to decrease calcium. Isn't that what we wanted? Isn't that what we wanted? Because we started with hypercalcemia, so we need to drop the blood calcium, and we did. Now, when you look at the opposite, this is a very important loop that you need to understand, because you're going to find it in clinicals, you're going to find it in pharmacology when you move on to the other classes. If you look now into the opposite, so at the beginning we dealt with too much calcium, hypercalcemia. Let's now look at the opposite. Let's look at hypocalcemia. If you look at hypocalcemia, from the name hypo, that means there is a drop, significant drop. There's a drop in the calcium levels. This drop in the calcium levels, the drop in the calcium level is going to be detected by who? Chemoreceptors or osmoreceptors, mechanoreceptors, thermoreceptors, or photoreceptors. Is that clear? Who is going to be detecting that there is a drop in the calcium?
Is it the integration processes?
So the integration, processing, and control center is not going to detect. Detector is always receptor. These guys, they don't detect. They wait for the call center for 911 is not going to call you and say, is everything okay? Do you need the fire truck? Do you need the ambulance? Do you need the police? They're not going to call you. You call them. But once you call them, they're going to call on your behalf to solve the problem. So now we have a drop in calcium. Who's going to detect the problem? The receptor. Now we have many receptors now. We have chemoreceptor, we have osmoreceptor, we have mechanoreceptor, we have thermoreceptor, we have photoreceptor. Which receptor is going to detect that there's a drop in calcium?
Is it chemo again?
Yeah, it's going to be a chemoreceptor. And then the chemoreceptor is going to be sending out an input that is sensory and afferent. And you will see that this is a process that is going to be involving integration. And then who's going to be the control center? Is going to be the parathyroid gland. Is going to be the parathyroid gland. What is the parathyroid gland? You know, the thyroid gland looks like a bow tie in front of the neck. The parathyroid gland is like 4 buttons behind it. So this is the thyroid gland from the front anteriorly. But if you look at it from the back, it has 4 buttons. First button, second button, third button, and fourth button. This is known as the parathyroid gland. Parathyroid gland. That is the one that's gonna release for us the output, the motor output through an efferent neuron, and we will see that, you know, a hormone. This time, are we going to secrete calcitonin again? In the beginning, we secreted calcitonin because there was a increase in calcium. But now there's a decrease in calcium. So we're not going to secrete calcitonin because that's going to make situation even worse. It's going to deplete even more calcium from the blood. So now we're going to secrete parathyroid hormone. Parathyroid hormone. And that is now going to dump a lot of calcium it's gonna break. It's not gonna dump. It's gonna start scratching the bone. It's going to start to scratch the bone, and it's going to liberate bone powder and calcium, making the calcium fall from the bone into the blood. So now the arrow is gonna point out from the bone into the blood, and now the calcium level is gonna be increased. Are we clear? Okay. So now we're gonna look at these three variables: fluid, electrolyte, and acid-base balance. So that means we're gonna need a system. Okay, is everybody paying attention? If we look at these three variables, fluids, that means we need a system for when it's too much water or too little water. We need to detect that. If you're running a marathon, how do you know you're thirsty? Because that system was activated. The system for fluid balance was activated to tell you, hey, blood volume went down because you've been running the marathon. You've been sweating a lot and you have lost a lot of water. And the opposite, if you drink too much water, there's going to be a satiety reflex that you're not thirsty no more. So that's because of the fluid system. Electrolyte system, that's the system we just talked about. If there's too much calcium, too little calcium, too much glucose, too little glucose, too much potassium, too little potassium, that's a separate system. And the third system is acid-base balance. You don't want to suffer from acidosis because that's going to lead to death. We talked about that when we did the respiratory system. We said that if something is wrong with the lungs because the patient is smoking cigarette, or because the patient has lung fibrosis, or because the patient has COPD, you see that they're unable to expel the carbon dioxide. Carbon dioxide is going to build up in the lungs, and then that's going to increase the blood acidity. So that's going to cause acidosis. And the opposite, you cannot remove too much carbon dioxide more than you're supposed to, because what's going to happen to the blood pH is going to increase, and that's going to be alkalosis now. So we don't want acidosis, we don't want alkalosis, we don't want hyperkalemia, we don't want hypokalemia, we don't want hypercalcemia, we don't want hypocalcemia, we want moderation. So now let's look at these systems and how they work. Okay, so the water percentage is different when you compare women versus men, children versus adults, adults versus the geriatrics, the very old. So a newborn's baby's body weight is 75% water. So the total body water content of you guys, average age, young adult, men have 60% water and women have 50% water. Why is that the case? Because women tend to have more lipid in their structure, in the anatomy of the tissue structure. The adipose tissue, the adipose fat connective tissue is a lot more in female compared to males. So the obese and the elderly people, they have less water in their bodies due to the fat and the lipids displacing the water. So we need to now divide our body into different compartments. We see that if you examine the body, we have an intracellular compartment, we have an extracellular compartment. Intracellular compartment is basically the cytoplasm. So let's look at how is water distributed. How is water distributed in the cytoplasm compared to the rest of the body compartments? So what are the body compartments? Well, we have inside the cell, so all the water that's in your body. So for men, 60%, for women, 50%. That 50% for men, that's 60% for men, and 50% for women is not actually in one place. You have the body compartments are inside the cell, known as intracellular fluid compartment. That means inside intracellular fluid compartment. That means it's inside the cell, meaning in the cytoplasm. And you have another compartment, and that is known as the extravascular compartment. This extravascular compartment, this is where you have your extracellular compartment. This extracellular compartment is itself divided into interstitial compartment and extravascular compartment. Interstitial compartment meaning that it's the compartment that is between the cells in the tissue. So you have interstitial compartment, and you have 25% that is in the interstitial fluid, and you have, so 25% is in the interstitial fluid, and then 8% is in the intravascular compartment. This is inside the blood vessel. Intravascular compartment. That is inside the blood vessels. And that is about 80%. And lastly, you have in the transcellular compartment. Transcellular compartment is the, from the name, transcellular. So that is squeezed between the cells that make up the tissue. Example of that is your cerebrospinal fluid, the synovial fluid, the peritoneal fluid, the pleural fluid, the pericardial fluid, the vitreous and the aqueous humor of the eye. These are all fluids that are known as the transcellular fluid. And these represent about 2% of the total body water that is found outside the cell. So if you see now, we have different directions for the flow of water in the blood. You begin by drinking a cup of water. Drinking that cup of water means that the water has now entered into did it enter to the respiratory tract? Did the water enter through your integumentary, the skin? Apparently not. The water went inside your digestive tract. So the water went into your oral cavity, then into the esophagus, and now the water is inside your stomach. If the water is inside the stomach, the water is going to flow into the intestines, and then the intestines are going to absorb the water from the intestine into the blood. And the blood is the site of regulating the water. So water is now gonna move from the bloodstream into the tissue compartment. So the same way the blood is gonna deliver oxygen to the tissue compartment, the same way blood is going to remove carbon dioxide from the tissue compartment, the same way blood is going to deliver nutrients, hormones, neurotransmitters to the tissue compartment. Blood is also going to deliver water. Because remember when we did the blood lecture, we centrifuged the blood and we learned that the plasma compartment is about 55% of the entire total blood volume. And this 55% is actually majorly water with a little bit of proteins and electrolytes. So this water is now going to be delivered to the tissue compartment. And then the tissue compartment is going to take as much as it needs until it reaches homeostasis. Then the rest of the water is going to be sent back to the blood compartment, and the rest of it is going to go into your lymph compartment. And the lymph compartment is going to take the blood water back into your right heart. So we need to balance fluids that are in our body. So when the daily water gains and losses are equal, that means you are at fluid balance. You have not lost more water than you gained, and you have not gained more water than you have lost. That means you are in a state of balance. Now, how do we gain water? We gain water through two ways. The first one is metabolic water, and then there's preformed water. Preformed water is the water that is essentially part of your diet. So when you eat a sandwich, this sandwich was not entirely solid. There is water that is preformed inside this bread that you're eating. There is water preformed inside the steak that or the chicken that you ate. So that's your food is actually one of the sources of water. So when you're eating, you're also supplying water to your body, not only when you're drinking a cup of water. Metabolic water is the water that is a byproduct of metabolism. Remember when we did the metabolism lecture, we realized that when we perform catabolism, we use water for hydrolysis to break apart these micromolecules in order to generate ATP, to break the bonds, to use energy and endothermic reaction so the energy can flow out in what's known as an exergonic reaction. A byproduct of that is the usage of water. Now, if we want to perform anabolism, we want to go the opposite direction. If we want to go from a monosaccharide into a disaccharide, or from a disaccharide into a complex polysaccharide, here we don't perform hydrolysis. Here we perform dehydration. Dehydration is when we remove water from the micromolecules in order to join them together and form the glycosidic bonds for sugars and form the peptide bonds for proteins. This water that's going to come out, that's an example of metabolic water that is formed by the metabolism and the dehydration synthesis. Now, this is the route for water gain: preformed water and metabolic water. Now, what are the routes of losing water? How do we lose water? Obviously, you lose water through urine. That is the main route for regulating fluid balance in the body. If you have so much water in your blood pressure is going high because the blood volume has increased and the cardiac output has increased, the contractility has increased, stroke volume has increased, then your urinary system is gonna free that stress, that defect of too much water in the blood, and then you're gonna urinate and you're gonna remove all of that water, which is now gonna restore. It's gonna drop the blood volume, so you're gonna drop the cardiac output, drop the stroke volume, drop the contractility, and drop the blood pressure. So if it wasn't for your urine, if it wasn't for the kidneys, you will not be able to remove this excess water that's in the blood. We also have insensible water loss. Insensible water loss is the water loss that you're not usually aware of. So in breath and cutaneous transpiration, you have so for example, if you hold a mirror, have you ever spoke so close to the mirror and you saw that there's water that's coming out of your mouth? That's an example of the insensible water loss. So the water loss that comes out when you're speaking, the water loss that comes out when you're breathing, it's a little bit, but it does exist. It depletes your body. That's why people who speak for a living, like teachers, they always need to drink water after their session. Then there is the sensible water loss, and that we talked about. This is your urination. And then there's the obligatory water loss. This is the output that is unavoidable. This is the water that comes out with the waste, the fecal matter, and the expired air. There you go. Typical daily water gains and losses in a state of fluid balance. So if you usually, so now let's compare how much water is inside our body and how much water gets lost. 1,600 milliliters, about a liter, more than a liter and a half, is taken and required every single day when we are drinking the water. Then there is 700 milliliters of water, that is when we are eating fruits and vegetables. And then there is the metabolic water, that is a byproduct of the dehydration and the anabolism, when we are storing large complex macromolecules. On the other side now, let's look at the water loss. The water loss is 200 milliliters lost in the fecal matter every day. 300 milliliters is lost when you are expiring, breathing, and talking. Sweating takes about 100 milliliters of water, while the most amount of water loss is through the kidneys and the bladder and in the urination. So the osmoreceptors, they are responsible for detecting the osmolarity of your blood. Our homeostatic osmolarity range is 300 milliosmoles. If you're more than 300 milliosmoles, that means you're becoming hyperosmolar. So if the osmolarity is more than if the osmolarity is more than 300 milliosmoles, if the osmolarity is more than 300 milliosmoles, we see that this is a state of hyperosmolarity. And you know, we always discuss that when there is a hyper, that's a problem. So that means an input signal is going to be sent to your brain in the hypothalamus, and the hypothalamus is going to turn on and activate, is going to turn on and activate the thirst response. The thirst response. It's going to turn on and activate the thirst response. You're going to be drinking a lot of water. Now, if you look into the opposite, when there is hypo, you guys have a question? If there is hypoosmolarity, that is when there is a drop in the osmotic balance, and here we need to send an input and turn off. So if there is hyperosmolarity, we drink water. If there's hypoosmolarity, that means there's too much water and we need to turn off and inactivate the thirst response. And inactivate the thirst response. So if we look in this figure here, compare somebody who is suffering from dehydration. So you guys see where my mouse is? This person is apparently in the desert. See the desert, the sand, the cactus. It is so hot. Now this person now is apparently suffering from dehydration. Are they suffering from hypervolemia or hypovolemia? Hypervolemia, that means the blood volume is too high. Hypovolemia means the blood volume is too low. Somebody in the desert, do you think that person who's suffering from dehydration has hypervolemia or hypovolemia? Hypovolemia, because the blood volume is dropping because they're sweating too much. What about osmolarity? Are they going to have hyperosmolarity or hypoosmolarity? Person in the desert dying, sweating, is that going to be hyper or hypoosmolarity? Hyperosmolar, because when you add water, you dilute the solution. When you remove water, you make the solution really osmolar. So now you see here, there is an increased blood osmolarity, and here we're suffering from reduced blood volume. And if you have a low blood volume, what's going to happen to the blood pressure? If somebody has a low blood volume because they're sweating too much, they're in the desert. They're going to have kidney stone because the blood is deficient in water, and the electrolytes are going to get sticky and clump up, and they're going to have a kidney stone. But how does that going to affect the blood pressure? Somebody whose blood is deficient in water, someone who's suffering from hypovolemia, are they going to have high blood pressure or low blood pressure?
Low blood.
They're going to have very low blood pressure. They are on the path for shock. So your body is not going to sit around and watch the blood volume drop. Your brain is not just going to sit there and watch the osmolarity skyrocket and do nothing about it. Your brain is not going to sit there and watch the blood volume drop. You're about to enter shock, and the brain is just sitting there watching, doing nothing. So the brain needs to take two actions. One action for the blood osmolarity that's going so high because you're losing water, and the other action is for the blood pressure that is dropping so severely because your blood volume is low, your blood pressure is low, your stroke volume is low, your contractility is low. So now let's look at how the brain solves those two problems. The first problem is the increased osmolarity. Obviously, there's going to be a receptor who's going to detect that the osmolarity went up or down. For somebody who's dehydrated in the desert, that the osmolarity went up. So you see, it stimulates hypothalamic osmoreceptors. What is that going to lead the brain to do? Number one, reduced salivation. So you're not going to be salivating, because if you don't have water in your body, you cannot afford to lose any more water. Because salivation, saliva, is 99% water. So you're going to shut down salivation to conserve the water that's in the blood. We cannot afford to make saliva from the water in our blood. And you're going to have dry mouth because there's no saliva. So that's why people who are dehydrated, their mouth is like really dry and white. What about the other problem? The drop in blood pressure. Remember, we talked about that last week. The renin-angiotensin-aldosterone axis. This axis is very, very important. You're going to see it in pharmacology because many medications interfere with this axis in order to restore eutension. A patient who has high blood pressure are going to take angiotensin receptor blockers, ARB. Angiotensin receptor blockers are interfering with this right here, renin-angiotensin-aldosterone system, in order to restore the blood pressure. We're going to see now how. Also, patients who have high blood pressure, they take medications known as ACE inhibitors, angiotensin converting enzyme inhibitors, because angiotensin converting enzyme inhibitors are going to cause a drop in blood pressure. So let's look at the renin-angiotensin-aldosterone system again. You guys really need to understand this system, because if you move past AMP2 and you do not know this system, you're going to suffer in pharmacology and you're going to suffer in clinicals. So let's see now, how does the RAS system operate? How does the RAS. What is RAS? R AAS. What is RAS? RAS stands for renin. Renin. A stands for angiotensin. Angiotensin. The other A stands for aldosterone. Excellent. Aldosterone. And S stands for, I'm sorry? System. Very good. So how does it work? This system only works when there is hypo or hypertension. When there is a hypotension. So if there's hypotension, that means there is a minus drop. There is a drop in blood pressure. So the blood pressure went down. There is a drop in blood pressure. Hypotension. Are we clear? A drop in blood pressure. That is known as hypotension. If there is hypotension, is this a problem or not? Is hypotension a problem or is it okay? Hypotension. A drop in blood pressure. Minus. When the blood pressure drops. Is this something okay or is it a problem? It's a problem. So when there is a problem, who's responsible for detecting that there is a problem? Who does that? The receptor. So, and you know we have different kinds of receptors. But what is the name of the receptor or the detector that is going to detect that blood pressure dropped? Is it a thermoreceptor, mechanoreceptor, chemoreceptor, osmoreceptor, photoreceptor, nociceptor? What kind of receptor detects that blood pressure drop? Chemo. Chemo is for a chemical. Like glucose went up, that's a chemo. Carbon dioxide, oxygen, that's a chemo. But it's pressure. Is pressure a chemical? Pressure is not a chemical. What is pressure? So look at the list of your receptors. We have thermoreceptor. What is that for? Thermoreceptor. It's for temperature. Do we need a thermoreceptor for pressure? No. Chemoreceptors. Those detect chemicals. Can chemoreceptors detect pressure? No. Is mechano. Why do mechanoreceptors detect pressure? Because they are responsible for the mechanics. The mechanics. So when there's a stretch receptors, mechanoreceptors, proprioceptors, they detect that the blood vessels are being dilated because blood is hitting them so hard, blood pressure is so high, so they detect the pressure sensation. So here we're going to have mechanoreceptors. So mechanoreceptors are going to detect that the blood pressure is so high. Then the mechanoreceptors are going to send in information to the kidney, and the kidneys are gonna send renin. Renin is a very important enzyme. What is renin going to do? Renin is going to convert some raw angiotensinogen. Renin is going to convert angiotensinogen into what? What is renin going to convert angiotensinogen into? So remember, I've mentioned to you in the past that if we have nogen If you have angiotensinogen, if you have nogen, that means you're off. It means you're inactive. You're inactive and off. Angiotensinogen is off. So what is renin going to do? It's going to remove the nogen and it's going to convert it into angiotensin 1. Angiotensin 1. This angiotensin 1 has been made possible due to the effects of renin. Renin converted angiotensinogen into angiotensin 1. Then angiotensin 1 is going to travel to the lung. It's going to go to the lungs. And what's happening in the lungs? In the lungs, there is a very important enzyme known as ACE. ACE. A-C-E. What does ACE stand for? ACE stands for angiotensin 1. Angiotensin 1. C stands for converting, and E stands for enzyme. So this enzyme here, ACE, what is ACE going to do? Angiotensin 1 converting enzyme. What is it going to do? It's going to convert angiotensin 1 into angiotensin 2, angiotensin 2 into angiotensin 2. And angiotensin 2 now is going to go into your brain, in the hypothalamus, and it's going to make you thirsty, so you can go drink water. It's going to go in your blood vessels, and that's going to cause high blood pressure. And lastly, it's going to go into your, so it's going to go into the make you thirsty, so you drink more water, and then it's going to go to the blood vessels, increasing the blood pressure by causing vasoconstriction. When you cause vasoconstriction, you increase the total peripheral resistance. Total peripheral resistance. And lastly, it's going to go into your kidneys, and it's going to shut down the urination. It's going to shut down the urination. So you see, stimulates hypothalamic osmotic receptors, and you're going to have reduced salivation, dry mouth, thirst, and then you drink water. That's going to cool and moisten the mouth, rehydrate the blood, and that's going to distend the stomach and the intestine, and that's going to inhibit. So when you drink the water, when you used to be thirsty, your stomach was so small. When you drink water, the stomach is going to be full of water like a balloon, so it's going to stretch. And when it stretches, that stretch receptor is going to send a signal to your hypothalamus that we're full. You don't need to make us thirsty no more, so the thirst response is going to be inhibited. Okay. And the last, as we said here, this renin-angiotensin-aldosterone system is going to cause thirst in the brain, is going to cause the blood vessels to contract, and it's going to secrete aldosterone. That's why we call it renin-angiotensin-aldosterone axis. So the last thing that it does is that it secretes aldosterone. And what is aldosterone going to do? Aldosterone is going to cause water retention through salt retention. Water retention through salt retention. There we go. This is aldosterone. Now, there's a very important enzyme known as ADH. antidiuretic hormone. So from the name you can guess what is this hormone all about. What do you think antidiuretic hormone does? From the name, anti, that means it opposes to, against. Antidiuretic hormone. So obviously it's a hormone that is anti something. What is this hormone anti? What is this hormone anti? Antidiuretic hormone. What does diuresis mean? Yeah. So when you have diuresis, it means that you're urinating. This enzyme is called antidiuretic hormone. That means it's a hormone that is what? Against diuresis, against urine formation. So this kind of enzyme, what do you think is going to be secreted? An enzyme that is secreted to stop you from urination. When do you think it's going to be secreted? When blood pressure is high or low?
Low.
When blood pressure is low. Excellent. Because you cannot afford to urinate and your blood pressure is low. Because the blood volume affects your blood pressure. If your blood volume is low because you're peeing a lot, you lose water, your blood pressure is going to drop. Very good. This antidiuretic hormone, when blood osmolarity is high, is it going to be secreted or not? It's not going to be secreted because the osmolarity is high. That means we're not dilute. It means we don't have water now. So that's a problem. So as the osmolarity drops, the ADH secretion is less and the kidneys reabsorb water, less water, and produce more urine. So this lowers the total body water and compensates for hypertension. So fluid deficiency is the fluid imbalance that arises when the fluid output exceeds the intake over a long period of time. There are two types of deficiency. There's a volume depletion and there's also dehydration. We talked about that. When you lose water, that's hypovolemia, which is okay because you're losing water and sodium at the same time. But when you're looking at negative water balance in dehydration, here you're losing water, but there is sodium in the body. Now, that's a problem now. Because in volume depletion, you lost both. You lost water and sodium in equal proportion. But in dehydration, you're only losing water in the sweat. But sodium is still in your blood. Now, that's going to cause hyperosmolarity. So there is no proportional loss. There is an improportionate loss. Okay. So the source of fluid balance. You have dehydration that affects all fluid compartments. Examples would be water loss from swelling and the sweat that is produced by capillary filtration. There's blood volume and pressure that's going to drop. And then the blood that absorbs tissue fluid to replace the loss. So if you look at the skin, how many layers is your skin?
Is it 3?
Very good, because there is a dispute. The third one, you know, the hypodermis, some schools, conventions, they think it's part of it. Some schools, they don't. But the one that they don't disagree with is that 2, which is the dermis and what's the other layer in your skin? The dermis and the The epidermis. Which one is on the top? The dermis or the epidermis?
Epidermis.
The epidermis is at the top, and below it is the dermis. Then the hypodermis is all in the bottom. That one is important for fluid balance because you lose water through your epidermis. So that's why when you guys did the integumentary system in AP1, you, your professor, you guys went over that. You went over how your integumentary system is part of your immune system. How is your integumentary system part of your immune system? Yeah. So the sweat glands, you mean the dermacidins, like this burning detergent that is going to burn the bacteria, the acid mantle on the surface of your skin? Yes. And the skin is like a fence. It's like a, immune, people think immune is like you have to be white blood cells. No, that is a different type of innate immunity. Just by having a big fence around your house, you protect yourself from thieves, right? So your skin is the biggest fence, a mechanical fence. Some countries, they have big mountains, so the enemy can never enter their home and attack them. You understand? So, disorders of fluid balance. Now, we don't want to have too much water. That's going to cause increase in cardiac output. And you see that if your blood volume goes below 4 liters, that's known as hypovolemia. What if your blood volume goes to, you will die long before your blood volume becomes 3. Okay, guys, this figure here is very important. What is this figure showing you? It's showing you that 4 liters of blood, if you go below that, you're going to have hypovolemia. If you drop to about 3.3, you're going to die. Not even 3 liters. You're going to die long before you reach 3 liters. That's why a stabbing wound and a gunshot wound kill the patient. Why? Because their blood volume dropped to below 4. Your blood volume is supposed to be 5 liters. You cannot lose more than 1 liter of blood. If you lose half a liter, it's a big problem. Let alone you lose a whole liter, that's it. You have hypovolemia. You're going to need saline ASAP. And if you drop below 4 liters, that's going to become, that's going to cause death. Fluid sequestration. You're going to have excess accumulation of fluid in a particular location. And here, an example of that is going to be edema. Edema is when there is an accumulation of fluid in the interstitial spaces. And that's the most common form of fluid sequestration. That happens a lot to patients who have congestive heart failure. Patients who have congestive heart failure. Congestive heart failure is a big problem. Why? Because the blood is waiting in line. There's an obstruction of blood passage, and the blood is waiting in line to get to the heart. But because some defect is in the heart valve, we're not pumping the blood as hard as we want. The blood has waited for too long, then some of the water is going to start leaking out from the intravascular compartment into the nearby tissue compartment. Pleural effusion is when the fluid accumulation in the pleural cavity is caused by some lung infections. Now we're going to go into the electrolyte balance. We're going to look at the major cations: sodium, potassium, calcium, magnesium, and hydrogen proton. And we're going to look at the major anions: chloride, bicarbonate, and the phosphate. How does your body regulate them? Now, if you look at your blood plasma, well, obviously, your blood plasma is outside of the tissue cells. Your blood plasma is outside of the tissue cells. So these are two different compartments. So the blood plasma now is going to have different distributions of sodium. So inside the cell, there's too little sodium. You see in the intercellular, that means inside the cell. So inside the cell, there's too little sodium, but outside the cell, the blood plasma is too high. Inside the, potassium is too high in intercellular fluid compartment and is too low in the plasma compartment. Chloride is too high, just like sodium, and you see, nonetheless, you guys, this figure is very important because it shows you that the osmolarity is 300 milliosmoles in both the intracellular fluid compartment and the blood plasma. Both of them have the same 300, but the composition is different. Outside the cell, more sodium. Inside the cell, less sodium. Outside the cell, less potassium, calcium, and magnesium. Inside the cell, less calcium and chloride. But inside the cell, there is more phosphate and more potassium. Outside the cell, there's more chloride. But the combination of all of these electrolytes give you the same osmolarity. This figure is very important. Okay? Now, beginning with sodium. Sodium is very important and it is found more outside the cell. You guys learned about sodium in the action potential. So when you open the sodium channels, a lot of sodium is going to influx to the inside of the cell. And the sodium potassium ATPase, this enzyme channel that is utilizing the hydrolysis of ATP in order to move sodium back to where it came from against concentration gradient and move potassium down concentration gradient. So there we see, that's the action of aldosterone. So hypotension is gonna, you see, this is what we talked about earlier. If there's a drop in blood volume, renin is gonna be secreted, is gonna convert angiotensinogen into angiotensin. That's going to stimulate the adrenal cortex to secrete aldosterone. And then aldosterone is going to increase sodium reabsorption and water retention. We talked about the antidiuretic hormone that is going to modify the water excretion rate independently of the sodium excretion. Now, when we look at potassium, potassium is closely related to sodium in that both of them are regulated by your sodium potassium ATPase. And the snake venom, digoxin. The snake venom, if you get bit by a snake, God forbid, what's going to happen to you? It's going to shut down the sodium potassium ATPase channel. So here we see that electrical signaling in the nerves and the muscle cells is going to be affected. And we've seen in the past figure, you see here, that potassium is the predominant electrolyte inside of the cell. Now, when we look at potassium homeostasis is closely linked to sodium homeostasis, where 90% of potassium is found in the glomerular filtrate and it is reabsorbed by the proximal convoluted tubule, as we saw in the lecture on Monday. And aldosterone is going to stimulate the renal secretion of potassium. Now, what are the clinical implications and the pathogenesis of potassium imbalance on the membrane potentials? We see that these are the effects of potassium imbalances on the membrane potentials. So look at calcium. Calcium has functions that lend to the strength of the skeleton. Your bones integrity is strong due to your calcium deposition. If you have vitamin D, if there's no vitamin D, all the milk that you're drinking is going right outside your digestive tract. It is because your vitamin D, your active vitamin D, that is what's going to enable your intestine to reabsorb calcium to the intracellular compartment. So the cells maintain very low intracellular calcium levels in order to prevent calcium phosphate crystals from precipitating. These cells must pump calcium outside, and they keep the intracellular concentration low, or sequester calcium in the smooth endoplasmic reticulum and release it when needed. Calsequestrin is a protein that binds calcium and keeps it unreactive. So about 54% of magnesium is in the bone and about 45% in the intracellular fluid. So most intracellular magnesium is complex with ATP. So functions of chloride. It is the most abundant anion in the extracellular fluid. It is the major contribution to extracellular fluid osmolarity. It has a major role in the bodily pH. And something special about chloride is cystic fibrosis. Anybody knows what cystic fibrosis is? Cystic fibrosis. What is cystic fibrosis? What is cystic fibrosis? Yes. Excellent. So it's a genetic disorder. This genetic disorder eventually gonna lead up, excellent, like what you said, to a buildup of mucus plug. But there is a missing piece. How does it do that? It does that because it prevents the synthesis of chloride channels. So now you only have sodium channels. I have a video on that. I'm gonna assign it for you guys like a out of class assignment. So you gotta watch that video and you're gonna summarize it and then upload it to Brightspace, and then I will give you credit for that. Okay, I'm gonna read it and I'm gonna grade it. So cystic fibrosis is very important. And the reason that they call it cystic fibrosis is because it was first found as fibrotic cyst in the pancreas. It was first found as fibrotic cyst in your pancreas. Those fibrotic cysts in your pancreas, are they the only clinical problem that happens to a patient with cystic fibrosis? So if a patient has cystic fibrosis, all they're suffering from is fibrotic cyst on the pancreas? Absolutely not. They are suffering also from infertility. They are suffering from osmotic imbalance. They are suffering from neurological defects. But they call it cystic fibrosis because it was first discovered as these fibrotic cysts. Okay. So inorganic phosphates of the body fluids are in an equilibrium mixture of phosphate. And you know this phosphate is basically, what is phosphate? Phosphate is a buffer. Is a buffer that is found inside the cell to protect the cell from excessive increases in acidity or basic. So you need to understand something. What is the normal pH for the blood? What is the normal pH for your blood? It's a range from 7.35 to 7.45. This is the perfect pH at which your tissues are going to survive. Now, in order to ensure that we have this appropriate pH, we need a buffer system. We need a buffering system that has a buffering capacity, preventing severe drop or severe increase in the blood pH. So let's look at how does that happen. So this is the acid balance base. Okay. So in order to understand acid base balance, we need to understand what is an acid, what is a base. What's the difference between an acid and a base? What is the difference? What's an acid, Nicole? Who knows what's an acid? An acid, yes.
Acid are substances who release hydrogen and bases who access hydrogen ions.
So the acid is a substance that secretes hydrogen protons. Excellent. And what did you say the base was?
Which accept the hydrogen.
Accept. Excellent. So the hydrogen proton is secreted by the acids, and the hydrogen proton is absorbed and accepted by the bases. There's another definition for the base, and that the base can also donate what? OH, hydroxyl ion. Okay, Nicole, what is an acid?
You're asking me.
No, because I asked you, she responded, we say the answer, and you not paying attention. So pay attention so that you can learn. What is an acid and what is a base? Ekta was nicely enough to describe for us an acid. An acid is a chemical substance that donates hydrogen proton, and a base is a substance that accepts the hydrogen protons from the acids, and the base also has the capacity to donate hydroxyl ions. Well, this relationship between the acids and the bases must be tightly regulated by the buffers. Because remember, our blood cannot afford to be too acidic or too basic. We will die. If the blood is too acidic, that is known as acidosis. If the blood is too basic, that is known as alkalosis. The strong acid ionizes freely. It gives up most of the hydrogen proton ions, and it markedly lowers the pH. The weak acid ionizes only slightly. It keeps most hydrogen in a chemicals bound form that does not affect the pH. Strong base has strong tendency to bind hydrogen proton and raises the pH. A weak base binds less of the available hydrogen proton and has less effect on the pH. We talked about that. An example of a strong base, you see the hydroxide ion. An example of a weak base is the bicarbonate ion. What do we call a weak acid and a weak base? What do we call a weak acid and a weak base? Buffers. Weak acids and weak bases are buffers. And that is what we rely on to survive for our life. Who protect us from having our blood too acidic and too basic is the buffers, who are weak acids and weak bases. So the buffer is any mechanism that raises the pH. There are physiologic that resist pH changes by converting a strong acid or base to weak one. So the body has both physiological and chemical buffers. So physiological buffers, that's a system that stabilizes the pH by controlling the body's output of acids, bases, or carbon dioxide. The phosphate buffer system is a solution of phosphates, and as in the bicarbonate system, reactions that proceed to the right liberate hydrogen proton and decrease the pH. Is your respiratory system supportive in maintaining a pH balance in your blood? Absolutely. We talked about that in the respiratory system. When your blood pH is so low and you have acidity, what do you notice happens to your breathing rate? You hyperventilate because you're shunting off, expelling, and removing carbon dioxide. And then your pH is gonna go up to the physiological 7.3 to 7.4. You need to remember that. You need to remember the physiological pH. Okay, if you now look at your blood pH is between 7.45 to 7.35. If you're below 7.35, that causes acidosis. And if you go above 7.45, that is known as alkalosis. So you need to stay within this range. And that is known as the physiological pH. That is known as the physiological pH. So if your pH drops too low, what's gonna happen? You're gonna hyperventilate. You're gonna remove the carbon dioxide in the breath. What about urination? If your pH is too low, you're gonna urinate and remove acid. So somebody who is suffering from acidosis, if you do urinalysis and you examine their urine, what are you gonna find? What are you gonna find? If somebody has high acidity, you look at their urine, you will see a lot of acid in the urine. So your urinary system is a buffer system. Your respiratory system is a buffer system. And you also have the proteins. How do proteins look like? Proteins are made up of amino acids. Amino acids have 4 terminals: north, south, east, and west. North is hydrogen. South is the R substituent. And this is the acidic terminal. And that is the basic terminal. So how does that work? How does the amino terminal participate in the acid buffer system? Well, the acidic terminal is this one. This is your acidic terminal. So whenever your body is suffering from alkalosis and it needs hydrogen proton, the acidic terminal will say, there we go, I'm happy to give you a hydrogen proton because I'm an acid and I give hydrogen protons. And if your body is suffering from alkalosis, what is that going to happen? Your base, your amino terminal is going to say, I'll be happy to accept hydrogen proton. Are we clear? Okay, you can neutralize 2 or 3 times as much acid as the chemical buffers. So that's the respiratory system. You see expelling carbon dioxide. And we've seen that the urinary system, hydrogen proton in the blood is going to react with the bicarbonate ion to form carbonic acid. Then carbonic acid is going to decompose into water and carbon dioxide. That's step number 2. So this is step number 1. Step number 1 is a hydrogen proton in the acid blood is going to combine with the bicarbonate ion in order to give you carbonic acid. Carbonic acid is going to decompose into water and carbon dioxide, which is going to enter the tubules, the kidney tubules. Carbonic anhydrase, Ka, is going to combine the water and carbon dioxide to form, again, carbonic acid inside the kidney tubule. Then the sodium hydrogen proton antiport is going to take, which is going to return to the blood. So this carbonic acid is going to return into the blood. So the carbonic ion is spinning between the blood vessel and the kidney tubules. And when you remove it, you end up with carbon dioxide. This carbon dioxide now, the sodium proton antiport is going to exchange the hydrogen proton. It's going to exchange the hydrogen proton with sodium. Sodium is going to come inside the cell. Then you're going to have sodium carbonate from the glomerular filtrate here. That's step number 7. And then the sodium is going to be removed from the sodium potassium pump at the base of the cell, and it's going to react with the hydrogen proton from the tubule cell to the hydrogen proton to the carbonic acid. Okay, we discussed acidosis and alkalosis. And acidosis is when the pH of the extracellular fluid is below 7.35. You remember that. Acidosis, we discussed acidosis is when the blood pH is below 7.35. Hydrogen proton diffuses into the cell and arrives out of the derives out potassium, elevating the potassium concentration in the extracellular fluid. Alkalosis. The pH of the extracellular fluid is above 7.45. Hydrogen proton diffuses out of the cell and the potassium diffuses into the cell. So a person cannot live for more than a few hours if the blood pH is below 7. The relationship of the bicarbonate carbonic acid ratio, the pH. That shows you the normal range is between 7.35 to 7.45. Below that is alkalosis, below that is acidosis, above that is alkalosis. So you see now your body can never tolerate a drop in pH below 6.8. That's going to lead to death. And pH that is above 8, that is now going to lead to death also. So alkalosis, severe alkalosis is 8 and minimal alkalosis is 7.45. Okay, disorders of the acid-base balance, respiratory acidosis, that happens, as we said, to people with emphysema, lung problem. They cannot remove carbon dioxide, so carbon dioxide is sequestered in the lungs, and that is going to increase the overall carbon dioxide level in the blood and increase the acidity. Respiratory alkalosis is when you breathe so rapidly, you're hyperventilating, you're removing so much carbon dioxide. Now that led the pH to increase and it went above 8, and that may lead to death. Metabolic alkalosis, that is when there's an increased production of organic acids like lactic acid in aerobic fermentation, ketone body seen in alcoholism and diabetes mellitus. Metabolic alkalosis, that is rare, but it could result from the overuse of bicarbonates like antacids and the IV bicarbonate solutions. Compensation for acid-base imbalances. So the acid-base imbalances can be compensated or uncompensated. Compensated acidosis or alkalosis. So here either the kidneys are going to compensate for pH imbalances, and uncompensated acidosis, that means the pH imbalance is more than your body can tolerate. Compensated acidosis, it means that the kidneys are now operating to accommodate this loss and help, remove carbon dioxide. Or compensated alkalosis is when both your respiratory system and your urinary system are working together to restore the problem. But uncompensated or decompensated, it means that the problem is overwhelming and the acidity is so severe, or alkalosis is so severe, that there is a pH imbalance that the body cannot correct without clinical intervention. Respiratory compensation, we discussed that, and that is when there are changes in the pulmonary ventilation to correct in pH. Renal compensation, we discussed that, and that is when the kidneys are causing the acid to be removed in the urine, or preventing the acid from being shunted to the urine if you're suffering from alkalosis. So if you're suffering from acidosis, the kidney is going to remove the acid from blood to the urine. But if you're suffering from alkalosis, the kidney is going to remove the acid from the urine, sending it back to the blood to counter this elevation in pH. Fluid replacement therapy is when we restore and maintain proper fluid volume, composition, and distribution. Is a significant problem in a treatment of seriously ill patients. Okay, so we want to restore euvolemia. Don't want to restore hypovolemia. So fluids may be administered in order to replenish total blood water, in order to restore blood volume and pressure, in order to shift water from one fluid compartment to another. And this is the last slide. We see that excessive blood loss, we talked about that. Gunshot wound, stab wound. What happens? The blood volume must always be 5 liters. If you drop about a liter, then that's definitely a state of clinical intervention and you're suffering from hypovolemia. If you drop below 3.2 liters, you will die. So that's why we need the fluid replacement therapy. It's going to raise blood volume while maintaining normal osmolarity. And remember, if a patient is suffering from hypovolemia, we don't just give them water. We give them water with electrolytes. That's why when you're running, this Gatorade is very important. Why? Because when you were running, did you only lose water or did you also lose salt with the water? When you were running a marathon or exercising, were you only losing water or were you also losing, in addition to the water, salts? You were losing salt also. So you need to replenish both. You need to replenish water and you need to replenish salt. That can be used to correct the pH imbalances, and acidosis are treated with Ringer's lactate solution, while alkalosis is treated with potassium chloride. Any questions? Anybody has any question? All right, so that was chapter 24. Monday is the exam for both chapters. Go over all the questions in chapter 23 and chapter 24. The lab practical is only 15 questions. That's your last chance to get 100. And if you get 100, you will qualify for a makeup of your choice. Let me make sure that I got everybody in attendance. Okay, this was November the 17th. Alright, so today is the 19th. Zaisha is here, Shane is here, Runice is here, Shikenzie is absent. Nicole is here. Live is here. Lillian is here. Abby is here. Sehrish is absent. Penelope is here. Tulsi is here. Natalie is here. Adrian is here. Erin. Natalie is here. Amaya. Ariana. Ekta. Prashi. Isabella. Divyansh. Amapola is absent. Okay. All right, guys. Bye bye. See you next week. Lecture?
Yeah,
What do you mean? Lecture? You don't make it?
I don't have the labs and
Oh, no. The labs in person. Only the labs that you can do at home are the virtual labs. Bye bye.
Bye-bye, Professor.
Last week?
I sent you an email because I was in the hospital. I didn't get a chance to do it.
Yeah, because you know the labs you have to be in person here. So those ones you cannot do them from outside. But the virtual labs you can. So those ones, so the ones you missed from last week is just because, yeah, those are in person. You cannot go to make them in another lab. You have to be
Okay.
in here.
All right.
But just do excellent on the exam and you'll be fine.